Calculus Made Easy by Sylvanus P. Thompson and Martin Gardner, the first complete revision in over 75 years of the million copy bestseller, includes many new problems. Calculus Made Easy. Calculus Made Easy, being a very simplest introduction to those beautiful methods of reckoning which are generally called by the terrifying name of the differential calculus and the integral calculus. Sylvanus P. Thompson, Fellow of Royal Society, and Martin Gardner, newly revised, updated, expanded, and annotated for its 1998 edition. Content: Preface to the 1998 edition, page number 1. Preliminary chapter by Martin Gardner. What is a function? Page number 10. What is a limit? Page number 18. What is a derivative? Page number 30. Calculus Made Easy by Sylvanus P. Thompson. Publisher note on 3rd edition prologue. To deliver you from preliminary terror, page number 39. On different degree of smallness, page number 41. On relative growing, page number 45. Simplest cases, page number 51. New stage, what to do with constant, page number 59. Sums, differences, products and quotations, page number 66. Successive differentiation, page number 79. When time varies, page number 83. Introducing a useful dodge, page number 94. Geometrical meaning of differentiation, page number 103. Maxima and minima, page number 116. Curvature of curves, page number 132. Partial fraction and inverse functions, page number 139. On true compound interest and law of organic growth, page number 150. How to deal with sine and cosine, page number 175. Partial differentiation, page number 184. Integration, 191. Integrating as a reverse of integration of differentiating, page number 198. On finding area by integrating, page number 1, page number 210. Dodge pitfalls and triumph, page number 227. Finding solution, page number 235. A little more about curvature of curve, 249. How to find the length of an arc on a curve, page number 263. Table of standard form, 276. Epilogue and apologue, 279. Answer to exercise 281. Appendix, some recreational problem relating to calculus by Martin Gardner, 296. Index to 326. About the author, 330. Preface to the 1998 edition. Introductory course in calculus are now routinely taught to high school students and college freshmen. For students who hope to become mathematicians or to enter professions that require a knowledge of calculus, such courses are the highest hurdle they have to jump. Study shows that almost half of college freshmen who take a course in calculus fail to pass. Those who fail almost always abandon plan to major in mathematics, physics, or engineering, three fields where advanced calculus is essential. They may even decide against entering such professions as architecture, the behavior science, or the social science, especially economics, where calculus can be useful. They exit what they fear will be too difficult a road to consider career where entrance routes are easiest. One reason for such a high dropout rate is that introductory calculus is so poorly taught. Classes tend to be so boring that students sometimes fall asleep. Calculus textbooks get fatter and fatter every year with more multicolored overlays, computer graphics, and photographs of eminent mathematics starting with Newton and Leibniz. Yet they never seem easier to comprehend. You look through them in a vain for simple, clear exposition and for problems that will hook a student's interest. Their exercise how has one Mathematicians recently portrayed the dignity of solving crossword puzzles. Modern calculus textbooks often contain more than 1,000 pages heavy enough to make excellent doorstops and more than 1,000 frightening exercises. Their prices are rapidly approaching $100. Why do calculus books weigh so much? Lynn Arthurstein asked in a paper on 20 questions for calculus reformers that is reprinted in Towards a Lean and Lively Calculus, Mathematical Association of American 1986, edited by Ronald Douglas, because he answered. The economics of publishing compels authors to add every topic that anyone might want so that no one can reject the book just because some particular item is omitted. The result is an encyclopedic compendium of techniques, example exercise, and problems that more resemble an overgrown workbook than an intellectually stimulating introduction to a magnificent subject. Teaching of calculus is a national disgrace. Steen, a mathematician at St. Olaf College, later declared too often calculus is taught by an inexperienced instructor to ill-prepared students in an environment with insufficient feedback. Leonard Gilman's writing on the college teaching scandals, Focus Volume 8, 1988, page number 5 said, the calculus scene has been execrable for many years and given the inertia of our profession, is quite capable of continuing that way for many more. Calculus has been called the topic mathematics most love to hate. One hopes this is true only of teachers who do not appreciate its enormous power and beauty. However, is a retired mathematician who actually enjoyed teaching calculus in this book, Great Moment in Mathematics. I found this chapter. Surely, no subject in earlier college mathematics is more exciting or more fun to teach than the calculus. It is like being the ringmaster of a great three-ring circus. It has been said that one can recognize the student on a college campus who have studied the campus. They are the student with no eyebrow. In a test on measurement and the incredible applicability of the subject, the eyebrows of the calculus students have receded higher and finally vanished over the back of their head. Recent year has been seen a great hue and cry in mathematical circles over way to improve calculus teaching. Endless conferences have been held, many funded by the federal government. Dozens of experimental programs are underway here and there. Some leaders of reform argue that while traditional textbooks get weightier, the need for advanced calculus is actually diminishing. In this popular introduction to the history of mathematics, you sadly writes, today the larger part of the mathematics has no or very little connection with calculus or its extension. Why is this? One reason is obvious: computers. Today, digital computers have become incredibly fast and powerful. Continuous function, which once could be handled only by slow analog machine, can now be turned into discrete function, which digital computer handle efficiently with step-by-step algorithm. Handheld calculators called grapher will instantly graph a function much too complex to draw with a pencil on a grey graph paper. The trend now is away from continuous maths to what used to be called finite maths, but now is more often called discrete maths. Calculus is steadily being downgraded to make room for combinatorics, graph theory, topology, knot theory, group theory, matrix theory, number theory, logic, statistics, computer science, and a raft of other fields in which continuity play a relatively minor role. Discrete mathematics is all over the scene, not only in mathematics but also in science and technology. Quantum theory is riddled with it. Even space and time may turn out to be quantized. Evolution operated by discrete mutation leaps. Television is on the verge of replacing continuous analog transmission by discrete digital transmissions, which greatly improve picture quality. The most accurate way to preserve a painting or a symphony is by converting it to discrete number which lasts forever without deteriorating. When I was in high school, I had to master pencil and paper way to calculate square root. Happily, I was not forced to learn how to find the cube and higher roots. Today, it would be difficult to locate mathematician who can even recall how to calculate a square root. And why should they? They can find the nth root of any number by pushing keys in less time than it would take to consult a book with tables of roots. Logarithm once used for multiplying huge numbers have become as absolute as slide rules. Something similar is happening with the calculus students. See no reason today why they should master a tedious way of differentiating and integrating by hand when a computer will do the job as rapidly as it will calculate roots or multiply and divide large number. Mathematica, a widely used software system developed by Stephen Wolfram, for example, will instantly differentiate and integrate and draw relevant graphs for any calculus problem likely to arise in mathematics or science. Calculator with keys for finding derivatives and integrals now cost less than most calculus textbooks. It has been estimated that more than 90% of the exercise in the big textbooks can be solved by using such calculator. Leaders of calculus reform are not suggesting that calculus no longer be taught. What they recommend is a shift of emphasis from problem solving, which computers can do so much faster and more accurately, to an emphasis on understanding what computers are doing when they answer calculus question. Our knowledge of calculus is even essential just to know what to ask computer to do. Above all, calculus courses which instill and student an awareness of the great richness and elegance of calculus. Although suggestions are plentiful for ways to improve calculus teaching, a general consensus is yet to emerge. Several mathematicians have proposed introducing integral calculus before differential calculus. A notable example is the classic two-volume differential integral calculus, 1936 to 37 by Richard Courant. However, differentiality is so much easier to master than integrating that this which has not caught on. Several calculus reformers, notably Thomson, W. Tucker, C. His Rethinking Rigor in Calculus in American Mathematics Monthly, Volume 104, March 1997, page number 231 to 240, have recommended that the calculus text replace the important mean value theorem with increase function theorem. On the mean value theorem, see my postscripts to Thomson chapter 10. The IFT states that if the derivative on a function intervals is equal to or greater than 0, then function is increasing on the interval. For example, if a car speedometer always show number equal to or greater than 0 during a specified interval of time, then during that interval the car is either standing still or moving forward. Stated geometrically, it says that if the curve of a continuous function during a given interval has a tangent that is either horizontal or sloping upward, the function on the interval is either unchanging or increasing. This change also has not caught on. Many reformers want to replace the artificial problem in traditional textbooks with problem about application of calculus in probability theory, statistics, and in the biological and social science. Unfortunately for beginning students not yet working in these fields, such practical problem can seem as dull and tedious as artificial one. More radical reformers believe that calculus should no longer be taught in high school, not even to college freshmen, unless they have decided on a career for which knowledge of calculus is required. And there are opponents of reform who find nothing wrong in the way calculus has been traditionally taught, assuming, of course, it is taught by competent teachers. In its February 28, 1992 issue, Science Investigator Project Calc, a computer-oriented calculus courses offered at Duke University, only 57% of its students continued on with a second course in calculus as compared with 68% who continued on after taking a more traditional course. A few students liked the experimental course, most did not. One student called it the worst class I ever took, and I described it as big exercises in confusion. Still another quoted in science as saying, I am very jealous of my friend in normal calculus. I would do anything to have taken a regular calculus with pencil and paper. Efforts are now on the way to combine continuous and discrete mathematics in a single textbook. An outstanding example is Concrete Mathematics 1984, revised in 1989, an entertaining textbook by Donald Ronald Graham, Donald Knet, and Orent Patashnik. The authors coins the term concrete by taking con from the start of continuous and crete from the end of discrete. However, even this exciting textbook presupposes a knowledge of calculus. American philosopher and psychologist William James in 1893 related to Theodore Flournoy, a Geneva psychologist, asked, can you name me any sample books on differential calculus which gives an insight into philosophy of the subject? In spite of the current turmoil over fresh way to teach calculus, I know of no book that so well meet James' request as the book you are now holding. Many similar efforts have been made with such titles as Calculus for the Practical Man, the ABC of Calculus, What is Calculus About? Calculus is Easy Way, The Easy Way, and Simplified Calculus. They tend to be either too elementary or too advanced. Thomson strike a happy medium. It is true that his book is old-fashioned, intuitive, and traditionally oriented. Yet no author has written about calculus with great clarity and humor. Thomson not only explained the philosophy of the subject, he also teaches his reader how to differentiate and integrate simple functions. Sylvanus Phillips Thomson was born in 1851, the son of a schoolteacher in York, England from 1885 until his death in 1960. He was a professor of physics at the City and Guild Technical College in Finsbury. A distinguished electrical engineer, he was elected to the Royal Society in 1891 and served as president of several scientific societies. Thomson wrote numerous technical books and manuals on electricity, magnetism, dynamos, optics, many of which went through several editions. He also authored popular biography of scientists Michael Faraday, Philip Reese, and Lord Kelvin. A devout Quaker and active Knight Templar, he wrote two books about his faith, The Quest for Truth, 1950, and A Not Impossible Religion, published posthumously 1918. He was much in demand as lecturer. He is said to be a skillful painter of landscapes. He also wrote poetry. In 1920, two of his four daughters, Jane Smith Thompson and Helen G. Thompson, published a book about their father titled Sylvanus Philip Thompson, His Life and Letter. Calculus Made Easy was first issued by Macmillan in England in 1910 under the pseudonym of F.R.S., initial that stand for Fellow of Royal Society. The identity of the author was not revealed until after his death. The book was reprinted three times before the end of 1910. Thomson revised the book considerably in 1914, correcting errors and adding new material. The book was further revised and enlarged posthumously in 1919, and again in 1945 by F. G. W. Brown. Some of these later editions, such as the chapter on the book, was further revised and enlarged posthumously in 1919 and again in 1945 by F. G. W. Brown. Some of these later editions, such as chapter on partial fraction, are more technical than chapter in Thomson's original work. Curiously, Thomson's first edition, with its great simplicity and clarity, is in a way closer to kind of introductory books recommended today by reformers who wish to emphasize the basic idea of calculus and to downplay tedious technique for solving problems that today can be solved quickly by computer. Readers who wish merely to grasp the essence of calculus and can skip the more technical chapters. and need not struggle with solving all exercise. The book has never been out of print. St. Martin Press published its paperback edition 1970. Almost all revised of the book's first editions were farewell. A reviewer from the Athenaeum wrote, "It is not often that it's fall to lot of reviewer of mathematical literature to read such a gay, boisterous books as this very simplest introduction to those beautiful methods of reckoning which are generally called by the terrifying name of the differential calculus and the integral calculus. As a matter of fact, professional mathematicians will give a warm welcome to book which is so orthodox and its teaching is so vigorous in its exposition." Professor E.G. Goder, a colleague, said in a letter to Thompson, "I am very pleased to hear that your little books on calculus is likely to be available for general use. As you know, I have been teaching the elements of this subject to junior classes here for some years, and I do not know of any other books so well adapted to give fundamental idea. One of the great merits of the book is that it dispels the mysteries with which professional mathematicians envelop the subject. I feel sure that your little books with its common sense way of dealing with elementary idea of the calculus will be great success. Many of today eminent mathematics and scientists first learned calculus from Thomson book. Maurice Klein, himself the author of massive work on calculus, always recommend it as the best books to give a high school student who want to learn calculus. The late economic statistician Julian Simon sent me his paper, not yet published, titled "Why Johnny and Maybe You Hate Maths and Statistics." It contained high praise for Thomson's book. Calculus Made Easy has been damned by every professional mathematician I have asked about it. So far as I know, it is not used in any calculus courses anywhere. Nevertheless, almost a century after its first publication, it still sells briskly in paperback, even in college bookstore. It teaches the system of approximation that makes quite clear the central idea of calculus, the idea that is extraordinarily difficult to comprehend using the mathematician elegant methods of limits. Later on, Simon asked the question, why don't high schools and college kids get to learn calculus the Thomson way? Answer: the Thomson system has an unremediable fatal flaws. It is ugly in the eye of the world-class mathematician who sets the standard for the way mathematics is taught all down the line. At the run of the mill college and high school teacher, and ultimately the students are subject to this hegemony of the aesthetic taste of the great. Thomson simply avoid the deductive devices that enthrall mathematicians with their beauty and elegance. I mentioned earlier a book titled "Towards a Lean and Lively Calculus." It contained paper by mathematicians who participated in 1986 conference at Tulane University on how to improve calculus teaching. Most of the contribution urged cutting down on techniques for problem solving, stressing the understanding of ideas, integrating calculus with the use of calculator, and scaling down textbook to leaner and livelier form. Now the leanest and liveliest introduction to calculus ever written in Thomson, Calculus Made Easy. Yet Peter Renz was the only mathematician at the conference who had the courage to praise the book and list it as a reference. The two most important concepts in calculus are function and limits, because Thomson more or less assumed that his readers understand both notation. I have tried in two elementary preliminary chapters to make clearer what they both mean, and I have added a brief chapter about derivative here and there throughout Calculus Made Easy. I have inserted footnotes where I think something of interest can be said about the text. These notes are initialed MG to distinguish them from the Thomson notes. Where Thomson speaks of British currency, I have changed the value of dollar cents Terminology has been updated. Thomson uses the absolute term differential coefficient. I have changed it to derivatives. The term indefinite integrals is still used, but it is rapidly giving way to antiderivatives, so I have made a substitution. Thomson followed the British practice of erasing a decimal point to where it is easily confused with the dot that stand for multiplications. I have lowered every such points to conform to American custom, where Thomson used a now discarded sign for factorial. I have changed it to the familiar exclamation mark. Where Thomson used the Greek letter for epsilon, I have changed it to the English E. Where Thomson used the symbol log E, I have replaced it with an ln. Finally, in lengthy appendix, I have thrown together a variety of calculus-related problems that have recreational flavor. I hope my revision and addition for this newly revised edition of calculus made easy will render it even easier to understand, not just for high school and college students, but also for older laymen who, like William James, long to know what calculus is all about. Most mathematics deal with static objects such as circle and triangle and number, but the great universe out there, not made by us, is in a constant state of what Newton called flux. At every microsecond, it changes magically into something different. Mathematics, calculus is the mathematics of change. If you are not mathematician or scientist or don't intend to become one, there is no need for you to master the technique for solving calculus problem by hand. But if you avoid acquiring some insight into the essential of calculus, into what James call its philosophy, you will miss a great intellectual adventure. You will miss an exhilarating glimpse into one of the most marvelous, most useful creation of those small and mysterious computers inside our head. I am in debt to Dean Hickerson, Oliver Selfridge, and Peter Lenz for looking over this book manuscripts and providing a raft of correction welcome suggestion. Martin Gardner, January 1998. Preliminary chapter. What is function? No concept in mathematics, especially in calculus, is more fundamental than the concept of a function. The term was first used in 1673, letter written by Gottfried Wilhelm Leibniz, the German mathematician and philosopher who invented calculus independently of Isaac Newton. Since then, the term has undergone a gradual extension of meaning. In traditional calculus, a function is defined as a relation between two terms called variable because the value varies. Call the terms x and y. If every value of x is associated with exactly one value of y, then y is said to be a function of x. It is customary to use x for what is called independent variable and y for what is called a dependent variable because its value depends on the value of x. As Thomson explained in Chapter 3, letters at the end of the alphabet are traditionally applied to variables and letters elsewhere in the alphabet. Such words letters such as A, B, C are applied to constants. Constants are terms in an equation that have fixed value. For example, in y is equal to ax plus b, the variables are x and y, and a and b are constant. If y is equal to 2x plus 7, the constants are 2 and 7. They remain the same as x and y vary. A simple instance of a geometrical function is the dependence of square area on the length of its sides. In this case, the function is called one-to-one function because the dependency goes both ways. A square side is also a function of its area. A square area is the length of a side multiplied by itself. To express the area as a function of the side, let y be the area, x the side. Then write y is equal to x squared. It is assumed, of course, that x and y are positive. A slightly more complicated example of a one-to-one function is the relation of a square side to its diagonal. A square diagonal is the hypotenuse of an isosceles right triangle. We know from the Pythagorean theorem that the square of hypotenuse equals the sum of the square of other two sides. In this case, the sides are equal. To express the diagonal as a function of the square side, let y be the diagonal x the side and write y is equal to square root 2x square, or more simply y is equal to x square root 2. To express the side as a function of the diagonal, let y be the side x the diagonal and write y is equal to square root x square upon 2, or more simply y is equal to x upon root 2. The most common way to denote a function is to replace y, the dependent variable, by fx, f being the first letter of function. Thus y is equal to fx equal to x square, mean that y, the dependent variable, is the square of x. Instead of say y is equal to 2x minus 7, we write y is equal to fx and equal to 2x minus 7. This means that y, a function of x, depends on the value of x in the expression 2x minus 7. In this form, the expression is called an explicit function of x. If equation has the equivalent form of 2x minus y minus 7 is equal to 0, it is called an implicit function of x. Because explicit form is implied by the equation, it is easily obtained from the equation by rearranging terms. Instead of fx, other symbols are often used. If we wish to give numerical value of x and y in the example y is equal to fx is equal to 2x minus 7, we replace x by any value, say 6, and write y is equal to f6 is equal to 2 multiplied by 6 minus 7, giving the independent variable y a value of 5. If the dependence variable is function of a single independent variable, the function is called function of one variable. Family example: all one-to-one functions are the circumference or area of circle in relation to its radius, the surface or volume of a sphere in relation to its radius, the log of a number in relation to the number. Sine, cosine, tangent, seconds are called trigonometric function. Logs are logarithmic function. Exponential function are function in which x, the independent variable, is an exponent in equations such as y is equal to 2 raised to x. There are of course endless other examples of more complicated one variable functions which have been given name. Function R can depend on more than one variable. Again, there are endless examples. The hypotenuse of a right triangle depends on its two sides not necessarily equal. The function of a course involves three variables, but it is called a two-variable function because it has two independent variables. If z is the hypotenuse, we know from Pythagorean theorem that z is equal to square root x squared plus y squared. Note that this is not a one-to-one function. Knowing x and y gives z a unique value, but knowing z does not yield unique value for x and y. To the familiar example of a two-variable function, neither one-to-one are the area of triangle as a function of its altitude and basis, and the area of a right circular cylinder as a function of its radius and height. Function of one and two variables are ubiquitous in physics. The period of a pendulum is a function of its length. The distance covered by a dropped stone and its velocity are each function of the elapsed time since it was dropped. Atmospheric pressure is a function of altitude. A bullet energy is a two-variable function depending on its mass and velocity. The electrical resistance of a wire depends on length of the wire and the diameter of its circular cross-section. Function can have any number of independent variables. A simple instance of three-variable function is the volume of a rectangular room. It is dependent on the room, two sides, and height. The volume of a four-dimensional hyperroom is a function of four variables. A beginning student of calculus must be familiar with how equations with two variables can be modeled by curves on the Cartesian plane. The plane is named after a French mathematician and philosopher René Descartes, who invented it. Values of the independent variable are represented by points along the horizontal x-axis. Values of the dependent variable are represented by points along the vertical y-axis. Point on the plane signify an ordered pair of x and y number. If a function is linear, that is, if it has one form y is equal to ax plus b, the curve representing the ordered pair is a straight line. If a function does not have form ax plus b, the curve is not a straight line. Figure 1 is a Cartesian graph of y is equal to x squared. The curve is a parabola. Point along each axis represent real number, rational and irrational, positive on right side of x-axis, negative on the left, positive at the top of the y-axis, negative at the bottom. The graph origin point where the axes intersect represents 0. If x is a side of a square, we assume it is neither 0 nor negative, so the relevant curve would be only the right side of parabola. Assuming the square side is 3, move vertically up from 3 on the axis to the curve, then go to left to the y-axis where you find that square of 3 is 9. I apologize to reader for whom all of this is whole hat. If a function involves three independent variables, the Cartesian graph must be extended to three-dimensional space with axes x, y, and z. I once heard about a professor whose name I no longer recall, who liked to dramatize this space to his student by running back and forth while he exclaimed, "This is the x-axis." He then ran up and down the center as shouting, "This is the y-axis," and finally hopped up and down while shouting, "This is the z-axis." Function of more than three variables require Cartesian space with more than three axes. Unfortunately, a professor cannot dramatize axes higher than 3 by running or jumping. Note the label domain and range in Figure 1. In recent decades, it has become fashionable to generalize the definition of function. Values that can be taken by independent variables are called variable domain. Value that can be taken by dependent variable are called range. On the Cartesian plane, the domain consists of a number along horizontal x-axis. The range consists of a number along vertical y-axis. Domain and range can be infinite sets such as set of real number or the set of integer, or either one can be finite set such as portion of real number. The number on thermometer, for instance, represent a finite integral of real number. We use to measure the temperature of water. The number represents an interval between the temperature at which water freezes and boils. Here the height of the mercury column relative to water's temperature is as one-to-one function of one variable. In modern set theory, this way of defining function can be extended to completely arbitrary sets of numbers. For a function that is described not by an equation but by a set of rules, the simplest way to specify the rule is by a table. For example, table is in Figure 2 shows a set of arbitrary numbers that constitutes the domain on the left. The corresponding set of arbitrary numbers in the range is on the right. The rules that govern these functions are indicated by arrow. This arrow shows that every number in the domain correlates to a single number on the right. As you can see, more than one number on the left can lead to the same number on the right, but one not vice versa. Another example of such function is shown in figure 3 along with its graph consists of 6 isolated points in the plane. Because every number on the left lead to exactly one number on the right, we can say that the number on the right are function of those on the left. Some writers call the number on the right image of those on the left. The arrows to are said to furnish a mapping of domain to range. Some call the arrow correspondence rules that define the function. For most of function counter can calculate the domain consists of single interval of real number. The domain might be the entire x-axis as it is for function y is equal to x square, or might be interval that's bounded. For example, the domain of y is equal to arc sin x consists of all x such that -1 smaller than or equal to x, x is smaller than or equal to 1, or it might be bounded on one side and unbounded on the other. For example, the domain by y is equal to square root x consists of all x greater than or equal to 0. We call such function continuous if its graph can be drawn without lifting the pencil from the paper, and is continuous otherwise. The complete form definition of continuity, which is also applicable to function with more complicated domain, is beyond the scope of this book. For example, the three functions just recommended are also continuous. Figure 4 shows an example of a continuous function. Its domain consists of all real numbers, but its graph has infinitely many pieces that aren't connected to each other. In these books, we will concern almost entirely with continuous function. Though that if a vertical line from the x-axis intersects more than one point on a curve, the curve cannot represent a function because it maps an x number to more than one y number. Figure 5 is a graph that clearly is not a function because vertical lines such as the one shown dotted intersect the graph at three spots. It should be noted that Thomson did not use the modern definition of function. For example, the graph shows in figure 30 of chapter 11 failed this vertical line test, but Thomson considered it a function. In this generalized definition of function, the one variable function is any set of ordered pair of numbers such that every number in one set is paired with exactly one number of the other set. Put differently, in the order pair, no x number can be repeated, though a y number can be. In this broad way of viewing function, the arbitrary combination of a save or sequence of button to be pushed to open a door, a function of counting numbers. To open a safe, you must turn the knob back and forth to a random set of integer. The safe combination is say 2, 19, 3, 2, 19. Then those numbers are a function of 1, 2, 3, 4, 5. They represent the order in which number must be taken to open the safe, or the order in which button must be pushed to open a door. In a similar way, the height of tiny peaks along a cylinder locks keys are an arbitrary function of position along the key length. In recent years, mathematicians have widened the notation of function even further to include things that are not numbers. Indeed, they can be anything at all that are element of a set. Function is simply the correlation of each elements in one set to exactly one element of another set. This leads to all sorts of use of word function that seem absurd. Smith has red hair, John has black hair, and Robinson's hair is white. Their hair color is a function of the three men. Position of town on a map are functions of their position on the earth. The number of toes in a normal family is a function of the number of persons in the family. Different persons can have the same mother, but no person has more than one mother. This allows one to say that mother are function of person. Elephant mother are a function of elephants but not grandmother because an elephant can have two grandmothers. As one mathematics recently put it, function have been generalized up to the sky and down into the ground. Useful way to think of function in this generalized way is to imagine a black box with input and output opening. Any elements in a domain number or device is put into the box. Out will pop a single element in the range. The machinery inside the box magically provides the correlation by using whatever correspondence rules govern the function. In calculus, the inputs and outputs are almost always real number, and machinery in the black box operates on rules provided by equation. Because the generalized definition of a function leads to bizarre extreme, many educators today, especially those with engineering backgrounds, think it is confusing and unnecessary to introduce such a broad definition of a function to beginning calculus students. Nevertheless, an increasing number of modern calculus textbooks spend many pages on the generalized definition. Their author believed that defining a function as a mapping of elements from any sets of any other set is a strong unifying concept that should be taught to all calculus students. Opponents of this practice think that calculus should not be concerned with thought, town, mother, and elephant. Its domain and range should be confined, as they always have been, to a real number whose function describe continuous change. It is a fortunate and astonishing fact that fundamental laws of our fantastic fidgety universe are based on relatively simple equations. If it is were otherwise, we surely would know less than we know now about how our universe behaves. And Newton Leibniz would probably never have invented or discovered calculus. Preliminary Chapter 2. What is a limit? Is it possible, though difficult, to understand calculus without a firm grasp on meaning of a limit, a derivative, the fundamental concept of differential calculus is a limit and integral. The fundamental concept of integral calculus is a limit. This chapter will be in second video.